So I'm going to talk today about binding of sparse distributed representations in hierarchical temporal memory. HTM is a brain-inspired machine learning framework. It models the structure and circuitry of pyramidal neurons found in the neocortex. Specifically, the organization of these pyramidal neurons in the neocortex is the cortical column. And this is what HTM models as a region. The HTM neuron takes multiple sources of dendritic input, proximal, basal, and apical. We focus on the spatial puller, which processes the proximal or feed-forward input to these cells. And again, it takes a binary input. The input flows through these proximal synapses and activates a set of columns within the cortical column or region. This set of active columns is known as a sparse distributed representation, which can also be represented as a sparse binary vector. It's distributed in nature, non-localist, and resilient to noise. We propose a binding operation by using the second step in this algorithm, the inhibition step, to produce SDRs that are capable of being bound. And so I really haven't mentioned too much about what binding is, but the motivation behind binding, as we'll see, is that the binding operation is the basis for content addressable memory. We think this could help facilitate the long-term storage and retrieval of SDRs for HTM-based systems. Among other things, it can be also used to combine different modalities of data, again, without increasing dimensionality. So the binding is a neuroscience problem. The vision version of this problem is in two scenes that you see at the bottom here, a red square and a blue circle. There are different brain regions that encode shape and color. How do you not confuse the two different scenarios or scenes at the bottom here? How do you know it's a red square and a blue circle instead of a blue square and a red circle? And some solutions in this space are vector symbolic architectures. Of particular interest to us were Penty-Canerva's binary spatter codes because of their intrinsic similarity to HTM's SDRs, because they're both binary and in some instances sparse. So we scoured the literature trying to find a binding operation, and Canerva recently published, along with Leho in 2015, a binding operation on sparse binary distributed representations, exactly what we're looking for. And they do this by sectioning the vector into segments and ensuring that this vector is something known is maximally sparse. And so the way this operation works is just by simply bit shifting. You first section both SDRs into segments, ensuring that there's one active bit in each segment. Then you take your two vectors that you want to bind together, in this case A and B. You bind them together by shifting segment-wise to get a bound vector C that is the same dimensionality and sparseness. And consequently, if you wanted to unbind the complex vector, you can do this by giving either component vectors that you bound together, and you can recall or retrieve or index into this memory and get your other vector back. So one issue that when applying this operation to HTM is that HTM's SDRs are not maximally sparse by default. So our approach to this was to use to adjust the neighborhood mask in the spatial puller to sync up with, to section the SDR into segments. And by doing this, when we ran through the local inhibition portion of the algorithm, we got one active bit in each segment. We're a little bit stricter with how we choose which column becomes active. Also, the other half of this is that we needed to initialize the synapses or the connections from your columns to your input space. It's very much dependent on how your input space looks like. And so before I get into that, we wanted to simulate binding on a spatial data set. We chose a small norm for this, and we ended up using, to encode data for the spatial puller, it only takes in binary inputs. So we chose Freq to encode the semantic features in these images because it gives binary descriptors. And it also doesn't have backprop, so that's cool too. So because the Freq encoder encodes its image data, it kind of scales it from coarse-defined information, we can initialize a kind of a topology within local inhibition in that each segment kind of looks at a various portion of the descriptor. It's just sampled from a normal distribution that you shift along the indices. So we ran this on Spatial Norb, one epoch of training, and what we immediately saw was that kind of what we expected was that local inhibition it performs a little bit less in terms of quantitative metrics than kind of standard spatial polar implementations that use global inhibition. Again, this is because we're using a stricter inhibition rule. Columns that would normally become active don't necessarily become active because we need them to be maximally sparse so that we can bind these representations. If we look at the clusters, we can actually see on the right here, this is with our local inhibition, that we preserve in terms of blue more class similarity than if we just used global inhibition, where it's kind of spread out among the red and blue clusters, which I believe are animals and trucks. So now that we have vectors that are capable of being bound, we ran through two experiments to demonstrate this. The first experiment was binding various features with their corresponding azimuth or viewpoint around the object. And we generated these location vectors. We just randomly generated them. They are maximally sparse as well, and we bound them together into a bound representation. And for our second experiment, what we did was we summed these bound representations. You can think of it as a rotation around an object to get a more complex representation. And this is just a simple bitwise logical OR. And so if we look at the results of the first experiment, what you can see immediately is that there's 18 clusters of data. And these correspond to the specific 18 SDRs that we use to encode the location positions. There are some exceptions, as you can see, like right here. There is a limit to how separable these representations are, and it's really dependent on how much data you have, how big are your vectors, how sparse they are, and things like that. But the other main takeaway from this is that you can unbind or you can use this as content addressable memory, meaning that if you give an SDR or a location or an azimuth SDR, you can unbind some of these clusters and by asking the question, what feature is located at this azimuth? Or if you unbind with a feature SDR, you can ask what azimuth is associated with this feature. And if you ask an unrelated question, you'll get noise back. So the answer really won't make sense in the context of either components that are being bound together. And again, these are the same dimensionality and sparseness as both component vectors. So the second experiment, which is a little bit more interesting, is that if you look on the right here, we can see as we superimpose these bound representations together, and again, this is a supervised approach. We're explicitly binding these features together. We can see that we get kind of a more structured representation. Each particular string that you see kind of corresponds to a couple of sets of data points, which again is a rotation, is the sum of the features as rotated around the object. The different data points in each of those strings correspond, you can't see this from this legend, correspond to the different elevations. So again, what we see here is not only more class similarity, but instance similarity and elevation similarity. Even though we didn't necessarily give it any information about elevation, the TSNE algorithm kind of clustered those data points together. If we superimpose without binding, as you can see on the left here, there's a lot of noise in terms of how things are clustered together. There might be some similarity in terms of instances and classes, but that doesn't seem to be quite the case as we see on the right. In either of these plots, or sorry, superpositions, as soon as you start superimposing or logically ORing these sparse distributed vectors together, you don't get the same sparseness. Again, you get 300 and 800 bits out of around 2,000. So we're getting about 50% density in these vectors, which makes it difficult at this point to retrieve information from them. So just to quickly summarize, our method of local inhibition kind of serves for the basis of kind of content addressable memory that kind of naturally not naturally, but falls out of the HTM spatial pooler. Again, I think density is going to be a limiting factor in terms of recall if you are superimposing them. Thank you.
Thank you, Ahmed.